Hello everybody, and welcome to page 101 in the workbook. In this video, we're actually going to back up and look at the last two main theorems of this chapter, Theorems 13.3 and 13.4. We're going to start here, though, with exercise 3 and 4 because they're going to motivate very nicely what these theorems are saying. Okay, so I'm hoping that by now you've already made an attempt at these exercises, maybe taken a few minutes to check your solutions. Let's talk through the results of this exercise 3. Okay, so they asked us to kind of go back to exercise 2 and to look at each of those rings and to figure out what the additive order of the unity element was in each of those rings. Supposedly there's a relationship between that and the characteristic of the ring. Okay, let's look at the answers to this question and see if we can maybe notice the pattern that's going on here. And I'm going to start first with the rings that have non-zero characteristic. Okay, that's going to be everything except B. And what you might notice there is that the order of the unity element agrees with the characteristic in every single case. Okay, in the case of A, for example, the characteristic of Z4 is 4. We did that calculation together, and that also happens to be the order of the unity element in Z4. And you'll notice that that's true in the rest of these as well. Characteristic of Z7 and the order of the unity element in Z7 are both 7. Okay, and then the remaining case, in Z, we talked about how the characteristic of that ring is 0, and the order of the unity element happens to be infinite in that case. We can write down as many copies of 1 as we want to, add them all up, and we're never going to get 0. Okay, so it would appear then, you may have found a way to put this into words, that the characteristic of a ring is very closely related to the order of the unity element if it has a unity element. Okay, we'll state a theorem that kind of pulls all that together in a minute here. Okay, let's move on now to number 4, see what observation that's leading us to. Okay, so which of the rings in exercise 2 are integral domains? Okay, I'm hoping that you kind of went through those rings one by one and asked yourself which of those have the property of being integral domains and came up with 3 of them. Okay, Z, Z7, and Z2 adjoined X. Okay, and they ask us then, what are the characteristics of these rings? Okay, let's think about that one by one here. Okay, well, the characteristic of Z is 0. Okay, because of the fact that we've got elements of infinite order there. Characteristic of Z7 is 7, and Z2 adjoined X is 2. Okay, my question to you is, what's special about those two numbers? Notice that they both happen to be primes. Okay, that turns out to be no accident. Okay, it turns out to be a fact that if you start with an integral domain, there are only 2 possible things that can happen with the characteristic. Either it's going to be 0, like it was for Z, or it's going to be some prime number. Okay, so let's go back then to page 97 and take a look at the theorems that sort of pull those observations together for us. Okay, so starting with Theorem 13.3, okay, and this is again page 97 that we're looking at. Okay, so let R be a ring with unity 1. Okay, if 1 has infinite order under addition, then the characteristic of R is going to be 0. That's the behavior that we saw in the ring Z. And if, on the other hand, 1 has finite order n under addition, then that's going to be the characteristic of our ring. That's the behavior that we saw in the other rings. Okay, and then Theorem 13.4 tells us, that was the observation that we made in exercise 4, that the characteristic of an integral domain is always either 0 or a prime. Okay, now what I'd like to do is to take a couple of minutes to prove Theorem 13.3. You're welcome to look in the textbook and see the proof of Theorem 13.4 if you're interested. All right, and we've really got 2 claims that we're making in Theorem 13.3. We're going to prove those one at a time. So case 1 would be the case where 1 has infinite order. Okay, in that case, we're going to try to prove that our ring must have characteristic 0. Okay, well, if 1 has infinite order, that means that it doesn't matter how many copies of 1 we take. N times 1 is never going to be equal to 0. Okay, for any positive integer, okay, so there is no positive integer n such that x equals 0 for all x in R. Oh, not the reals, just the arbitrary ring R. Okay, and if you think about it, that's the definition of what it means. Okay, or that demonstrates that the characteristic of R has to be 0. Okay, so we've proven the first claim made in Theorem 13.3. What about the second claim? Okay, well, the other possibility is that maybe 1 has finite order. Okay, well, that means let's take that finite order and give it a name. We'll call it n. Let n be the additive order of 1. Okay, and we will take any element in our ring, we'll call it x. Okay, remember what we're trying to show here. We're trying to show that the characteristic of the ring is n. Okay, because n is the additive order of 1. So we just need to show that if we take n copies of x and add them together, we should get 0. All right, that's where we're trying to go here. All right, well, here goes. Let's see if we can do that. So if we look at n times x, by definition, that's just writing down n copies of x and adding them all together. Okay, so we'll make the note n terms that we're writing down here, or okay. And then we have a unity in this ring. Okay, it's called 1, so we can rewrite each of those x's if we want to as just 1 times x. Okay, and that's certainly equivalent to what we have above because 1 times x is still x. Then we're going to use the distributive property to rewrite that as 1 plus 1, okay, n copies of 1 added together times x. And notice by definition, taking n copies of 1 and adding them up, we can also write that as just n times 1 x. Okay, but then remember what we said at the very beginning, where this n came from. N is the additive order of 1. So we know that when we take n times 1, we're going to get 0. Okay, just by the definition of what that additive order means. Okay, and I'm going to write that into the proof because that's a very important step here. N is the order of 1. And 0 times x is equal to 0 in any ring. Okay, so what have we shown here? Well, we just showed that if we take n copies of x and add them together, we get 0. Okay, and does that show that the characteristic of the ring is 0? Is n? It does, provided that n is the smallest number for which we can do that. And the thing is, we started out with the assumption that n is the order of 1, which means that n is the smallest number that works for 1. And since it's the smallest number that works for 1, that's got to be the smallest number that works for all of the things in our ring. All right, so let's add that last sentence, and then we have ourselves a proof. Okay, since n was the smallest integer, okay, it follows that the characteristic of R has to equal n. Okay, so we've just proven that this number n, the additive order of 1, that's the smallest number that's going to work, Okay, that for every element in our ring, for which we can take n copies of any element in the ring, add them together and get 0. Okay, and we're done.